as reference material. I'll stop sharing. I'll share another bit. Okay. Stop sharing that tab. I'll share Professor Jane's notes on the experiment. So, this is a computational exercise. Use Planck's black body radiation equation law to draw radiation curves for black bodies at temperatures 7,508, 5,800, and 300. Try plotting the three curves on the same page on a common set of axes. If these are difficult, then of course, so this bit we have done. So part A has been done. Now, what we are interested in today is part B. Find the total emissive power by integrating each of the three curves by finding the area under the curves. Show that it conforms with Stefan-Boltzmann law. Okay, so the second part is integration. We have to integrate the curves, the area under the curves, so that we can find out how much power is contained in each of the curves. Now, we have learned last year a bit of how to do that integration by hand and also numerically using trapezoidal and the Simpson rules. Okay, so what we actually want to do today is to show you how you go about doing integration. Once we are done with how to go about doing integration using Python, especially using a module which is known as scientific Python, Scipy, which contains the stuff we need to use for integration, then it will now become possible for us to do the integration stuff. So I'm not only trying to show you, I actually need to teach you a bit of the Python module, how it works. Then after we see how it works with all the integration you have learned, the trapezoidal, the Simpson stuff, then we can now use it. We can use that module to try to solve this particular problem. Are we clear? On what we are trying to do. Yeah, so basically this thing is in, can you see? Okay, yeah, that's good. Yeah, so yeah, this is we're going to introduce you to scientific computing with Scipy, and it gives us a number of tools, algorithms for doing the kind of stuff we need to do. Scipy works with NumPy. Basically, you're going to be using NumPy, Matplotlib, and Scipy, excuse me, as three of them, like that. NumPy, we're going to use it for creating our arrays, which we basically vectors, since we're going to be making plots, so we're talking about vectors here. Sometimes you can also use NumPy to create matrices, which is used for linear algebra. Then Matplotlib is what you're going to use for making our plots, matplotlib.pyplot. Yeah, that's what you're going to use for making our plots. Then Scipy is what's going to provide us with the modules we need to do the integrations, the modules we need to do the interpolations, and all this other stuff which we have to do in our computational physics course. Okay, so the first thing we're going to do before we look at what Scipy can do, we have to create some arrays, and those arrays are going to be created using NumPy. So we're going to import NumPy as np. So we do that. hope people know how to do an import. It's necessary in this case. Let me just okay. So going to, maybe that's too much. How does it look that side? Okay, that's fine. I think it's fine. So we do an import. Then next we create an array of numbers from 0 to 10 in steps of 0.1 using the NumPy function arange. So we're going to start from 0 all the way up to 1 less than 1 less than 10, like that. Then we do a print. Why does it look like this thing has already run? Okay, let me do that. Restart and clear. Okay, so we import NumPy as NP, then we create our array X, then we print out the array. So these are the numbers we've generated, or we could actually say 10.1, like that, so that we only go up to 10, all the way up to 10. So those are the numbers we have generated. Of course, if you don't have an idea what this is, so we can find out what the type of X is, and Python is going to tell you that what you have is actually what's referred to as a NumPy array. So that's how you create arrays. And the reason why we need these arrays is because we can use these arrays for making other arrays based on a particular function. So in this case, with the NumPy, I access the function sign, so np.sign, then I give it X so that I can get the value of the sign of X, and I store that in the array Y. Then I print out the Y's like that. Then I can check the type. So basically, we have seen the bit where we typically use NumPy. So we use the NumPy for creating arrays quickly, arrays of numbers which you're going to use. The next bit is matplotlib. Now we use matplotlib for making graphs of our data. So in this case, we are going to import matplotlib, a submodule of matplotlib, not the whole thing, just a small part of it. So you're going to import this bit, matplotlib.pyplot as PLT. So we import, make this import. But, excuse me. Next, say plt.figure. So we create a plotting figure. So create a plot figure. Create a plot figure. Then of course, then plot. Then plot x against y. Then label x-axis, label or y-axis, label x-axis, then add grid, add square grid, add legend, so we're going to do this here. That, then say location as best, what the best is, then show plot. So stuff should work. So there is our plot. So this is where we use matplotlib for making quick, nice plots. Okay, I hope people still remember how to do this. So here we have got our x-axis, there is a y-axis, then this is the actual plot. We have added a grid, then of course that bit there. You can add a title, PRT, the title, plot of sine of x. Okay, so that it is that. So typically that's what you use matplotlib for making a nice plot. Are we clear?
Yes.
You have to remember that you're going to do this lab. Sorry?
Legend.
What? Legend is this bit. Explanation for what the line is. This bit here. That's what's called a legend. This. You've seen this? Explaining what this line is. This is the line for what? So that shows you it's the line for sine x. So that bit there which explains what that line is, that's what a legend is. Okay. Any other question?
No question.
Okay. So using NumPy, we created two arrays, x and y. Then using matplotlib.pyplot, we made a plot of these things. These two arrays. We've plotted the arrays x and y, and that's a plot, the way it looks like. Okay. The next thing now we need to introduce is what we need to look at itself, which is the Scipy. So we are going to import Scipy. So here, the Scipy module. So import Scipy module. Okay, that's been imported. Then after you import Scipy module, basically the next thing is what does Scipy bring to the table? Okay, so you can print out the contents of the Scipy module as a list. So you can say print dir then Scipy like that. So when you print out Scipy stuff, then you get a list of the stuff which is contained in the Scipy module. There's infinity here. What other stuff looks familiar? Add. There's add, a max, array max, a minimum, array minimum, angle, append, a range. This a range is the same a range which is in NumPy, which we used to create. Now, why is NumPy stuff showing up in Scipy? The reason why some NumPy functions are showing up in Scipy is because Scipy is based on NumPy. Is that clear? NumPy is used for building Scipy. So you will see that some of the functions which you know from NumPy, these are the same functions which you have in Scipy. Arccos, arcsine, arctan, array max, argument max, for finding out which thing has got a maximum. And we're going to use this for one of the things, because in our caves, Professor Jane wants us to find at what wavelength does the cave have a maximum. So you're going to give, like in the case in the case of the sine cave, you give it the values of y. So in this particular function, you give it the array y, which plots the y values. Then it's going to give you not the value itself, but it's going to give you the index which corresponds to that particular maximum value. So there's a lot of stuff there, okay, which you can have a look at. There's stuff which looks familiar. There's average, There's round, arctan. What else? What can you see? There's casts. There's this one here, ceiling, which rounds the number to up. There is stuff which looks familiar. For example, there's complex here, so there's a lot of capabilities for doing complex numbers. There is something called conjugate. That's the same conjugate, you know. Then there's convolve. There is also other functions. For example, here you've got this degree to radians, so it changes degrees into radians. You have got something which changes just degrees, so from radians to degrees. That's what I'm thinking. Then there is this bit here. This is for diagonal. This is for displacement, divide, some dots, data type, distack. What else? Other things are there. So I'm just trying to show you a bit of what's there. Which Scipy it's actually more specialized than NumPy, because NumPy is just normal mathematics stuff. Okay. Like that. Okay, so basically there's a lot of stuff. There is something which looks like log here. This is for load text, so you can have information which is in a file, then you can bring it into Scipy, logs and stuff. What else? Matrix. You can create a matrix, then you can start using matrix stuff. This is median here. Median has to do with statistics. So you can do statistical stuff. If there's median, there should be mean somewhere. This should be a mean here. So you can do statistical things, median, mean. Then this is a mesh grid for creating 2D plots, surfaces. So it has got capabilities for doing that. And where it gets the capability from Matplotlib for making such plots. Then it also has got ability for polynomials. There's this poly add, polynomial divide. This is very interesting here. Polynomial fit. So this polynomial fit is used for fitting a polynomial to data. So you have data, then you, like the way we have with the arrays x and y. So you give this function polynomial fit some arrays. Then you ask it to fit some polynomial of a certain degree, then it's going to try to do that. Polynomial values, like that, similar to what this thing does. So now it's going to give you the values of that particular polynomial and stuff like that. Okay. What other things? From poly, there is this bit here, rad to degrees. I think I've looked at something similar. Then there's radians here. There's quantile. That's something to do with statistics. But of also interest is this one, rand and random. These are for producing random numbers. Then there's remainder here. This is reshape. We know how to reshape a matrix, so you can do that. Then also, if you've got stuff, you can save your stuff. So you can save text, just save like that. Then what else? So there's shape here. There's sign here. There's sync, hyperbolic sign. There's square root here. If you want to do a square root of a number, you can use this function. If you want to square a number, you can also use that function. There's a function called subtract. There's a function called sum. If you want to add stuff, then of course there is tan here, hyperbolic tan. Then there's trace. Trace I think has to do with matrices. Then there's also trim. Triangular upper. If you want a triangular upper matrix, you can use this. What else? What else? What else? Yeah, so basically that's some of the stuff on the surface. However, the other thing I want to point out is that apart from just what's in this list, scientific Python itself is a big module. And usually when it comes to big modules, it means that they have got other modules inside them, something we call a submodule. So when you ask for help from Python, since you have imported SciPy like this, help SciPy, you have done an import of SciPy, then you ask for help, say help SciPy, then some documentation is going to come, and we just want to pay close attention to the stuff which comes at the beginning. Okay, so here help on package SciPy, name of the package, the name of the package is SciPy, a description, what does it do? SciPy, a scientific computing package for Python. Okay, contents. When you come under contents here, it says SciPy imports all the functions from NumPy. That's why this first sentence here says SciPy imports all the functions from NumPy. That's why you have NumPy functions showing up in SciPy, because it imports them, all of them. And additions provides the following. Apart from importing all the things which you can do with NumPy, there is also other stuff which are provided, which are only found in SciPy. Okay, so these are what are called sub packages, and the following sub packages are there. So use any of these sub packages require an explicit. So use of any of these packages requires an explicit export. For example, if you want to use any of this package, you have to import like this. Import scipy.cluster. So in this case, if you want to import this particular package, this is how it's supposed to be done. Scipy.cluster. Okay, so what kind of packages, sub packages does SciPy provide? So there's something called cluster. Cluster is used for something called vector quantization. Okay, means I have no idea what this is, but it's some stuff to do with mathematics. Then there's something called FFT. FFT, this is for fast Fourier transforms. We are going to use this in our computational physics. As we start our computational physics, when we start looking at Fourier transforms. So this FFT is a quick way of working out fast Fourier transforms. Then there's also a package, so discrete Fourier transforms. There's also another package called FFT pack, legacy discrete Fourier transforms. So basically legacy means old. These are a pack of old ways of doing Fourier transforms. The guy who is in business now is this guy, FFT, for the fast Fourier transform. Now, the thing which we are interested in is this bit here. There is a sub package called Integrate. This package called Integrate, sub package called Integrate, it's used for integration. It provides us with integration routines like trapezoidal, like Simpson, and all the other stuff which we didn't learn about last year. Okay, there is also another stuff package called Interpolate. This is used for interpolations. Okay, so we're going to see. We did not use this, but hopefully we're going to have one of the exercises probably where you can use it. Or if you don't use it now, then you can use it in the other course. Then there is another package called IO. This is used for data input and output, for getting data into SciPy and getting data out of SciPy. Then there is this bit here, linalg. This is used for linear algebra routines. So it provides you with stuff to do with linear algebra. Then there is this other package, linalg.plus. It's a wrapper. Then also there is this bit also, something similar. Then this is miscellaneous. Miscellaneous is basically the home for routines which do not have kind of like a bunch of miscellaneous stuff. Then there is another thing called nimage. This is used for handling images. If you want to do images, that's what it's used for. Then there is this ODR, orthogonal distance regression. I have no idea what that is, but it's there in SciPy. Then there is optimize. Now optimize is important because if you still remember what some of the things you did in optimize, that's where we had tools like bisection, Newton, Raphson method, and stuff like that, and also Brent. So those guys, they live in a module called optimize. Then if you want to do stuff to do with signal processing, there is a module called signal. So this provides signal processing tools. Then also signal.window. So this provides something called the window functions. Then there is space. This is for space matrices. Then space linear algebra. This is for space linear algebra and stuff like that. Basically, so yeah, useful stuff. Then of course there is also stuff to do with eigenvalues like that. Then there's spatial data structures. I think something to do with computers too much, but there's something which is important here. Spatial. This provides spatial functions, and also there is a capability which is there for doing statistics in SciPy. Stats. So there's a module called stats, and this stats module is used contains statistical functions. Okay, so you can see that SciPy, this module SciPy, when it comes to our computational physics course, is the go-to guy. If we really wanted, if you already knew Python, we could have just started the course with SciPy, and we can do everything with SciPy. Okay, any questions on what SciPy has to offer before we move forward?
No question.
Okay, I'm happy that people are clear. So the next thing we're going to do, as we are interested in solving a problem to do with integration. Are we clear? That's our interest. Our interest is to solve our problem with integration. Since we are interested in integration, we are going to go import this integrate subpackage. We're going to import subpackage integrate. So that's going to be, and how do we import these SciPy things? You have to be very explicit. You say import SciPy dot cluster. So in this case, it's going to be SciPy dot integrate. Okay. So with that, then we're going to do what we have to do. So we're going to import SciPy dot integrate. Submodule. There. So import SciPy dot integrate. Okay. Next, before we get help, we want to see the contents of SciPy dot integrate. List the contents of SciPy dot integrate. So I'm going to move it, these bits here, I'll move it a bit up. There. So what's there? Okay, so we look what's in SciPy dot integrate. So there's a bit of stuff. You look there. So we start with a complex ODI, that is ordinary differential equation. I think this is a composite trapezoidal. This is supposed to be double quadrant, quadrature, fixed quad, LS. I'm not sure. This one is the Newton cotes. It's one of the ways of doing integration. Then there's ODI, ordinary differential equations. So when we come to doing stuff with ordinary differential equations, you're going to come back to this guy. But of interest to us is there's this. This is a function for doing integration, quadrature. Using it, this is a step which is a process which we haven't looked at from our previous course. So try to stick to the things which we are kind of familiar to us. There is also here another quadrature. There is I think Robeng integration. Yeah, and also this one here. But the things which we know, there is this guy here. This is Simpson. There is also this guy here. Trap Z for trapezoidal. So our focus is really going to be on how to do trapezoidal integration, how to do integration with Simpson, and probably how to do using this guy, this quad, for quadrature integration. Okay, so you can always ask for help. If you need help, you find a lot of explanation on how this sim integrate works. So you start with, so you're going to be given an explanation, a small explanation of what this thing is. So what does Scipy.integrate do? So the name of the module is Scipy.integrate, description, integration, and ordinary differential equations. And that's how you access it. So inside here, what do the different functions contained there do? So here, quad, this does general purpose integration. The other thing which this one here, Romberg, this does integrate functions using Romberg integration. What else? Newton codes. This one, weights and error coefficients for Newton codes integration. So that's some kind of integration. But there are special cases of this Newton codes things which we are interested in, and there is this guy here. So this bit here, Trap-Z, use trapezoidal rule to compute integral, then cumulative trapezoidal, use trapezoidal rule to cumulatively compute integral. Then there is this bit here, use Simpson's rule to compute integral from samples. So basically our interest with what we know, with what we have learned, is how do you do trapezoidal integration, how do you do Simpson integration, and also how to use the other guy, this function up here. It's not very difficult to use. This bit here, quad, which does general purpose integration. So basically our focus is on these three functions: the quadrature, trapezoidal, Simpson, and also maybe Romberg integration. Okay. So let's start with the trapezoidal, composite trapezoidal rule. So if you want any help about this composite trapezoidal rule, so you have to, of course, you type Scipy, then integrate the name of the submodule, then later on the name of the function you're interested in, if you want help with trapezoidal like that. Are we clear? So you start with the name of the main module, which is Scipy, then you put a dot, then the name of the submodule in which the function is found, then you put a dot, then the name of the function. When you do that, then you are going to get some help on how to use trapezoidal. Now, help on function Trap-Z, trapezoidal in module NumPy. So you see where this function trapezoidal actually lives. The one thing you see from here is that it comes from NumPy. So Scipy imported this module, this function Trap-Z, from NumPy. Are we clear? Hello?
Clear.
Okay, so it imported the module from NumPy. That's the thing you see. But the next question is, how do you use trapezoidal? Well, you type Trap-Z, then you give it the y-axis, the array y. It's fine to give it the array y. If you have got x, you can give it x also. But if you don't have x, the array x, that's also okay. Then this bit, dx, remember, it has to create trapezoidals. So the trapezoidal thickness is going to be 1. That's what this dx is. The thickness of the trapezoids is going to create. as you give it whatever stuff k, whatever array you have given it, the trapezoidal thicknesses is going to be 1. Then this, of course, some stuff, but these have already been set for you, so you don't have to change anything here unless you want to do other things, but it's sufficient the way it is. You don't have to change anything. Okay, so, and also this has already been set, so this axis thing you don't have to set, you don't have to change it. The only thing which you really need is you need y. If you've got x, you can also provide x like that. So y is array like input to integrate, then x is optional also. X is your x values. The reason why your x values are optional most likely is because kind of this, I think it can still work with that. Okay, so basically, how do you use this thing? Well, you can say np.trapz, then you put in your values. So this is going to be your y values like that. Or you can say np.trapz. You're using np here because this thing is imported from NumPy. It lives in NumPy. So np.trapz. So you can do this, or so where these are your y values, or you can say np.trapz. You put in your array of y values, your list of y values, and you also put in your x values if you've got the x values. Otherwise, you can put in np.trapz. You can put in your y values. Then it's also possible that you can change the dx, the thickness, like this. From what it is to 1, you can change it to 2. So in our case, we are going to create a new x from 0 to 4 in steps of 1. So we create a new x like that. Then you print our x. Okay, so that's our x. Then we are going to create this array, y is equals to x squared. We're going to create this, y is equals to x squared. So that is going to be y is equals to np.power, then x to the power 2. Like that. Then we'll print out our y. There. Then we'll make a small plot to see what this guy looks like. Figure, create plot figure, legend. This I'll take down. Do a plot of x of what is it, x against y, x against y, make y label this side here, make x label, then here add a grid, then legend location paste, then show plot. We run this. So we run that. So basically this is what our y is, y against x. This is a plot. From 0 to 4 in steps of 0.1, and this is your y-axis, the y label this side, your y-axis, that's your x-axis, and this is your this is your legend. Now, if you integrate, if you do an integration which is from 0 to 4 of this function, basically what you're doing is when you're integrating, you're working out the area under this graph. Are we clear?
Yes.
Yeah, when you're integrating, you're just working out the area under a curve. So when you do that, if you do it by hand, if you don't know how to do it, I can show you. So here, so analytically, integral from 0 to 4 x squared is equals to dx. That's going to be x 2 plus 1. That's going to be 3. Then divide by 3. It's going to be like this. Then you put the limits of integration 0 and 4 like that. So you end up with this equals to 4 to the power 3 divided by 3 minus 0 to the power 3 divided by 3. So you end up with this. 4 to the power 3 divided by 3. Now 4 to the power 3 divided by 3, if you put it in this Python, print 4 to the power 3 divided by 3. 4 to the power 3 divided by 3 is this. 21.33, stuff like that. So this is the exact value of the integral. Are we clear?
Yes.
However, we can also do the same thing by employing our trapezoidal function. So the trapezoidal function, what we're going to do is we start with Scipy, the name of the module Scipy, then followed by integrate, the name of the submodule, then trapezoid, like that. Now, there are different ways you can do this. Either the first way, you can just do this. Just give it the value for y, the array y. If you do that, it will work out something. Does it? No. Mistake. If you put x. Okay. You have to put the x there. So if you do that, this is what you get. You get your 21.33, then a bunch of 9s. So basically, after this here, they differ a bit. But you can see that it's a very good approximation. Are we clear? Are we clear?
Yes, we are following, sir.
Okay. Next, you can also something similar. You can probably make your slices, your trapezoidal slices, much smaller. You can say the x. If you say trapezoidal slices are 0. Let's make very small slices. What do you get? That's too small. Okay. All right. There. If I put a dx value of 0.1, I get something which is okay. 21.34, like that. So basically, it's you having an idea of what the thing is supposed to be. Are we clear? So just putting your y this side, you put your y first, then your x gives you something which is okay, which is good. Are we clear?
We are clear.
Yeah, so that's how you do a trapezoidal integration. From trapezoidal integration, we're going to move on to Simpson's method. So again, something similar. We import. It's already been imported because it's in Scipy.integrate. We did an import of Scipy.integrate. Submodule. So Scipy.integrate, Scipy.integrate.simps. So this one, if you do that, you get a bit of some explanation also. Help on function sims in module scipy.integrate, then quadrature, something like that. Sims. This one, for it to work, you need to give it an array y. You can also give it x, that's fine. Then you can also give it a dx, but the dx has already been set, and the axis also has already been set. This other bit also has already been set up everything. So basically, it can work with just y. But if you've got x, there is no harm it can be done. You can also put the x there. So that's going to do Simpson integration. What other examples are there? So here, for example, there's a power thing. We have got this is the power 3, but with the power 2. So you just say integrate.sims y, then x, then you get something. Or you can put, yeah, basically just like that. So with whatever works simplest. So in this case, for an integral, if you're going to do this numerically, integral from 0 to 4 of x to the power 2 dx. So you're just going to say scipy.integrate sims, you put your y, you put your x, then you run it there. Now this is better because, as you can see, this is 21.33333333 like that. This is the same as the exact value from our integral when we worked it by hand. This bit, except at the very end there, 332. But our Simpson has got 33333 all over the place. So the Simpson one, as you can see, is better than the trapezoidal one. So if you're going to do integration cheaply, Simpson is a good choice. Are we clear? Huh? Is it clear?
Yes, it's clear.
So basically, this is how we do integration. We have to use whatever things we know, whatever stuff is familiar to us to do this stuff. Next, there is some kind of integration called Romberg integration, which we did not look at in our course. I think this is supposed to be, we'll probably try to do stuff like this. I don't know how much time we have. When we do our 4th year computational physics. One of the challenges which I'm facing is that from the course outline, like I was telling, is it Paul? Yeah, the one who contacted me. It's very, very difficult. If you look at the course outline, it's very, very difficult for you to figure out what it is you're supposed to teach. And in our case, when the lad who was teaching it passed on, I went into his office, I got some stuff, but there is still not enough material because some of the stuff which is already there is probably stuff which is very old, and I didn't have access. We don't have access to the person's computer, so there's stuff like that. So I really have to figure out which stuff, since I'm the only one who is doing this thing now, I really have to figure out what stuff is going to be taught at 3rd year and make a new course outline or whatever stuff, something like that, and what things need to go to 4th year. Because when I looked at some of the things you did in 3rd year, like curve fitting, actually curve fitting turns out was a 4th year topic. So there is all this thing which basically stuff we need to do. Anyway, with Romberg integration allows you to do integration using an actual function. The other ones you have looked at, trapezoidal integration and also Simpson integration, you are using an array. Perseverance, your microphone. So the other integrations you've looked at, trapezoidal and Simpson, you are using arrays y and x. So in this case, with Romberg integration, if you do not have arrays y and x, but you actually have the actual function, okay, if you have with the actual function itself, you can do that. So in this case, Scipy.integrate, then Romberg. When you do that, it's going to give you some help on how this function is used. So help on function Romberg in module Scipy Integrate Quadrature. So you start with the name of the function, which is Romberg, then you give it the function. After giving it the function, you give it the lower limit, the bottom limit. You also give it the upper limit of integration. Then some of these things have already been set, like the tolerance and the other stuff. So this other stuff, you don't have to touch it. The only thing you really have to concentrate on is this. What function are you giving it? And what is the lower limit? And what is the upper limit of the integration? That's the only thing you have to concentrate on. So in our case, we have our function here. Y is equal to x squared. So in this case, we create, since it's a small function, we create a lambda function. F, that's the name of the function, is going to be equal to lambda. Then our lambda function is only going to accept an x. Then what's supposed to happen with this x? So basically this x is going to be squared. So that's our little lambda function. So that's the function we're going to give. Then if you look at what we have here, so we've created the function that the limit of integration, the lower bit is 0, the upper bit is 4. So a is 0, b is 4. So you start with Scipy.integrate Romberg function is f a. Oh, okay. I already do that. So you can actually use positional arguments where you just put f there as a function, the name of the function. Then the next number here is going to be the lower limit of integration. The next one is going to be the upper limit of integration. When you do that, this is what you get. 21.333, then there's a 2 at the end there. So you can see that this 21.333 something 2 at the end is exactly as what we worked out by hand. The value we got for the integral when we worked it out by hand. This here. So Romberg integration. So we started with trapezoidal. Fine, it gave us something. Then we moved to Simpson, which was better than trapezoidal. Then we have moved on to Romberg integration, which is better than Simpson in terms of accuracy. Are we clear? Is it clear?
Yes.
Okay.
Yes, clear.
Good. Again, I want to point out that the nuts and bolts of how things are being happening, we are doing that. That's the stuff we do in class. Right now, what you have is a problem you have to solve with integration, and we are throwing out what solutions you can use. So as you're going to be doing your experiment, your lab, whatever solution you choose, that's up to you. You don't have to stick to what I've chosen. Okay, I'm showing you this is stuff we're supposed to do last year. This is how you do this integration, this is how you do this integration, this is how you do this integration. Okay. Next, you can also use keyword arguments. For example, the function, you can actually explicitly set function to f, then a to 0, and b to 4, like that. Then you run it, you get, so it works. So whether you use positional arguments or you use keyword arguments, this whole thing is going to work. Are we clear?
Clear.
Mm-hmm. The last method we're going to look at is what is referred to as quadrature integration. Quadrature integration basically works most of the time. So the help on quadrature integration is scipy.integrate then quad. Do that. So this is what you're going to get. So in this case, also it works like Romberg integration basically, except the keyword function keywords are different. The other one has got function, this one has got func here. So quad func A and B, where A and B are your limits of integration. But this one works generally fine most of the time. So in this case, and it also provides more information. For example, we're going to see the parameters. So these are the parameters. The func is the function. The A and B, these are limits of integration. A is the lower limit of integration. B is the upper limit of integration. That's basically the most important stuff. Then what are you going to get in return? So when you give when you give this quad a function, a lambda function, then you give it the upper and lower limits of integration, what is it going to give you? So basically, you're going to get a y integral from A to B. You're also going to get an error, absolute error, the error in your result. So you're going to get a value, y, the value for the integration, the integral itself. Then you're also going to get an error function, an error value between a value and whatever the actual thing is supposed to be. Then what other stuff? Then you're going to get something, this infodict, a dictionary containing additional information. So you're going to get some additional information. Then you're also going to get a message. This message is going to tell you whether there was convergence or not, whether things worked out or stuff like that. Then you might get some explanation. So you get a bunch of stuff. You get a lot more information about what has happened than these other things gave you. So in this case, we can start with this. For the same functions, we can say scipy.integrate, then quad, then the function is f, then 0 and 4. So in this case, when you do this, this is what you get. You get some additional information. So in this case, this is your actual integral, your y. So you're getting a tuple. This is the actual integral, your y, and followed by this number here. This number is the error in your integral. The error in the integral. Here, the y. The absolute error. That's the error, an estimate of the absolute error in the result. And if there is more information, you refer to the same help to see what the particular information is. So you can see what you have here, what you have been given is the value and also the error in the value as a tuple. If you are interested only in the value, if you are interested only in this particular value here, then you can access this value because what you have is a tuple using an index. Tuples like lists, the indices start from 0, then 1. So after you write this, we know that this bit is going to give you this. It's going to give you this tuple. But if you want to access only the first value of the tuple, which is the integral, then you can pass an index in square brackets, the index 0. That's what this is doing there. So when you do that, you just get your 21. This value which you have here as your 21, whatever 21 stuff is, you can actually, which is what you get from here, you can actually store it in a variable I for the integral, like that. Then you can display a nice message, say the integral is I, like that. Are we clear?
Huh? Yes.
There is also something you learned called tuple unpacking. Remember, when you say Scipy.integrate quad, then you do all this thing here. This thing gives you a tuple, but if you want your error and your integral to go straight into some variables you have defined, then you can do this. You create a variable I where this thing is going to go, the actual integral is going to go. Then you can also create this other bit here, the error, where the actual error is supposed to go, so that when you run that like that, then you do this, you get that. And when you want to find out the error, say the error is that's the error. You can do the same thing with argument, keyword arguments. No, quadrature integration. I need to change this here. Quadrature integration with keyword arguments. So you can do the same thing here. Now you can use the function, set it to F, A, set it to 0, B, set to 4. So you can do that. It works. Then, of course, if you want to access only the integral itself, then you add the index of the tuple, because the result of all these, this whole thing here, this gives you a tuple, which is this. So if you want to access the first item in this tuple, so you add the index in square brackets 0 there, so you get that. And of course, it's possible also to do the tuple unpacking, this I error, so that the first guy here, this first value is going to be stored in I, and this error value is going to be stored in the error thing here. So we can do a bit of a change like that, error, like that. Then here, the next, you have error. There. So we have come to the end of how we do integration. Is it clear? Of course, there is a recording of this thing, and also we are going to make the PDF available to people, and also the notebook itself. The recording is going to be posted on YouTube. The PDF will be posted in the Moodle. There will be a link also to this thing, which is going to be posted in your Moodle, where you can download the notebook. So basically, this is how you do numerical integration with Python and Scipy. Any questions? So next week, when we meet, we will finish up. Since we already have the plots, we already have the y's, the y values, we are going to mostly use, I think, Simpson. Simpson is going to give us something good. We're going to use the Simpson's methods to work out the integrals, the area under the curves at 7,000 kelvins, at 5,800 kelvins, and at 300 kelvins. Then after that, we will find out where the maximum is and what's the wavelength. Then we'll compare that with what you have for the Vin displacement law. Okay, unless there are any questions. So this thing is going to continue next week. So now that you have learned how to do numerical integration, next week we'll do part B and part C. Are we clear?
Yes.
Again, the thing is, I'm giving all this information, all these videos as the reference materials for you to answer the lab. So you pick out of this thing, you pick what is important for you. What do you need for you to create the curves? What do you need? What methods of integration are you going to use? You have to do that. Me, what I have to receive from you, you have got my WhatsApp lines. What I have to receive from you are notebooks showing what you have done with your name properly typed, your computer number, so that I can mark these things. Everything which I've shown here is not necessary for you to do your labs, but what I'm providing is information which you need for you to successfully do your labs. Are we clear? Yes. So people should, so at the end of the day, because Professor Jane wants his results for the labs, and we don't have the results for the labs. So we're going, since things can go up to we're going to use this month and probably next month. I don't know how many labs we're supposed to do, probably 5 or something. This month and next month, we'll try to do this stuff. I'll try to be as useful as possible as I can. Trying to explain how things are done with Python, so that you guys can see how stuff is done, so that you can also successfully carry out these things with Python. As most of you are experiencing, Python is not difficult. It's a very, very beautiful language to use. And also, you don't have to struggle a lot with the nuts and bolts of everything. Okay. So I think we are done. I need to prepare for another class. So I'll see you next week. Yeah, we are done. So I need to start preparing for a first year class I have at 17. So I will see you people next week. And also, I think those who are taking computational physics, I think probably after next week, I will have figured out exactly what I need to teach and what I don't need to teach in the computational physics course, so that we can get started. Yeah. All right. So, yes.
Before you go, sir, I'm not on Moodle. I'm currently on Astria, so I don't have the link for the lab. Then also, is it only on Friday when we'll be meeting, or the other days?
No, it's only on Friday. Someone, are you in the WhatsApp group?
Yes, I am.
Okay. So the link is the one which you have here. Can someone copy this link for the meeting?
Oh, no. In fact, someone sent it to me. Is it the same that we'll be using throughout?
Yes, it's the same that we'll be using throughout. We'll not be changing any links.
Okay.
Yeah.
Okay, thank you very much.
All right. So see you next week.
Okay, bye.
Yeah.